Assalamu alaikum warahmatullahi ta'ala wabarakatuh. This is the fifth lecture in lipid metabolism, and we are going to discuss metabolism of acylglycerols and sphingolipids. Our objectives is to revise or refresh our memory regarding the chemical structure of acylglycerols and sphingolipids, to outline the pathway of synthesis of both triacylglycerol and sphingolipids and their catabolism, particularly through lipases, and to outline the regulation of synthesis of triacylglycerol and phosphoglycerol, outline the pathway for synthesis of sphingolipids, and discuss examples of biomedically relevant disorders. Regarding synthesis of triacylglycerol, this is the structure of triacylglycerol, the glycerol backbone, and there's three acyl chains or three fatty acids. In position 1, we have a saturated fatty acid. In position 2 and 3, we have desaturated fatty acids. Synthesis of triacylglycerol proceeds through 4 steps. Triacylglycerol and phosphoglycerols are formed by acylation of triose phosphates. So this links lipids and carbohydrate metabolism. Glycerol and fatty acids, the initial substrates for triacylglycerol synthesis, has to be activated before they can be incorporated into the structure of an acylglycerol. So how is fatty acid activated? We have already come across activation of fatty acid. We said it is by being converted to acyl-CoA, then acyl-CoA synthetics. How is glycerol activated? By a kinase, a glycerol kinase, which will add a phosphate group to glycerol at position 3 to have a glycerol 3 phosphate. Glycerol kinase, the enzyme, is not expressed in the adipose tissue, which is a unique feature or aspect of this tissue and this enzyme. The second way of activation glycerol is from the glycolytic intermediate dihydroxyacetone phosphate by glycerol 3-phosphate dehydrogenase, and this is the alternative or the solution for the adipose tissue. So instead of having glycerol kinase, it can have glycerol, an active glycerol 3-phosphate by from the dihydroxyacetone phosphate intermediate of glycolysis. So this is glycerol 3-phosphate, glycerol with phosphate at position 3. It is obtained either from glycerol by glycerol kinase or in the adipose tissue from dihydroxyacetone phosphate by glycerol 3-phosphate dehydrogenase. And a question for you here is that adipose tissue lacks glycerol kinase. Instead, it uses glycerol 3-phosphate derived from dihydroxyacetone phosphate. This is a brilliant metabolic setup. Gives 3 justification for this statement. The second step in triacylglycerol synthesis is formation of phosphatidate. 2 molecules of acyl-CoA combine with glycerol 3-phosphate to form phosphatidate, which is a 1,2-diacylglycerol. So it is a glycerol backbone with 2 acyl residues for position 1 and 2. Formation of phosphatidate is actually a two-step reaction catalyzed by acyl transferase. So glycerol 3-phosphate, active form of glycerol, in two-step reaction by glycerol 3-phosphate acyl transferases will be successfully phosphorylated at position 1 and at position 2 to form 1 acylglycerol, and then at second position to form 1,2-diacylglycerol. R1 and R2 refers to the acyl residues, the fatty acids that are now being linked to the glycerol backbone. And the structure of phosphatidate, phosphatidate is also, of course, a phosphatidic acid. Phosphatidate is the simplest glycerol phospholipid. So the smallest or the initial or the first component of glycerol phospholipids is phosphatidate or phosphatidic acid. It consists of a glycerol backbone, 2 fatty acid chains, as we said, at position 1 and 2, in addition to a phosphate group, usually at position 3. So it is a 1,2-diacylglycerol phosphate. It is a 1,2-diacylglycerol with a phosphate at position 3. This is structure of phosphatidate, the glycerol backbone, fatty acid chain at position 1, fatty acid chain at position 2, in addition to phosphate group at position 3. So it is 1,2-diacyl phosphate. What is the function of phosphatidate? Actually, it is many functions, and among the most important ones are being a common precursor for the synthesis of triacylglycerols, many phospholipids, and cardiolipids. Phosphatidate can also act as a signaling molecule or a second messenger, which is needed for many regulatory functions in the cell. Phosphatidate is also needed for membrane dynamics because it affects membrane curvature, and it is involved in vesicle formation and fusion events. This is phosphatidate, synthesized from glycerol 3-phosphate. As you can see, phosphatidate here is a parent molecule for diacylglycerol, for cardiolipin, and phosphatidylglycerol, which will, in their turn, will give rise to phosphatidylcholine, phosphatidylethanol, triacylglycerol, and phosphatidylinositol for 5-phosphate. So phosphatidate is a parent molecule for all of these phospholipids and glycerols. The fourth step of triacylglycerol synthesis is formation of diacylglycerol from phosphatidate. Phosphatidate will be converted to 1,2-diacylglycerol by a phosphatidate phosphohydrolase with hydrolysis and release of inorganic phosphate. 1,2-diacylglycerol is formed. In the fourth and last step of triacylglycerol synthesis, diacylglycerol is esterified to triacylglycerol. So a third acyl residue or fatty acid is added by a diacylglycerol acyl transferase. The source of fatty acid will be an acyl-CoA, of course, an active fatty acid in the form of acyl-CoA. CoA will be released and the fatty acid will be added here at position 3 to form 1,2,3 triacylglycerol. And now we have our final product, triacylglycerol. Regarding the synthesis of phosphoglycerols or glycerol sphingolipids are either formed from phosphatidate, particularly phosphatidylinositol, or from 1,2-diacylglycerol. And particularly here, the ones that uses 1,2-diacylglycerol are phosphatidylcholine, phosphatidyllethanol, and phosphatidylserine. And as you can see here, that 1,2-diacylglycerol phosphatidate can, by a two-step reaction, can lead to the formation of phosphatidylinositol, while phosphatidylserine, phosphatidylethanolamine, phosphatidylcholine are formed from 1,2-diacylglycerol, which itself is formed from phosphatidate. How is triacylglycerol and phosphoglycerol synthesis regulated? Biosynthesis of both triacylglycerol, phosphatidylcholine, phosphatidylethanolamine is regulated by the availability of free fatty acids. The free fatty acids that escape oxidation are preferentially converted to phospholipids. So at any time, all the processes are taking place, however, not at an equal rate or at a steady rate. There is continuous breakdown and synthesis of triacylglycerols in the adipose tissue. The released fatty acid is mainly oxidized for energy. The surplus or the fatty acids that are not oxidized, the first option will be for them to form phospholipids. When the requirement of phospholipid is satisfied, then the surplus fatty acids will now be used to form triacylglycerols. Catabolism of triacylglycerol and phosphoglycerol. We start by discussing catabolism of triacylglycerol. An important fact to remember about breakdown of triacylglycerol is that it is not the reversal of synthesis. It starts with hydrolysis with a suitable lipase to yield free fatty acid and glycerol. The free fatty acid will be released in circulation bound by albumin. Albumin is a method of transporting fatty acids in the circulation. It will be taken either for oxidation, as we said, or esterification. What happens to glycerol? Glycerol utilization depends on the availability of glycerol kinase. Tissues that have glycerol kinase, like the liver, the kidney, intestine, mammary gland, can of course phosphorylate glycerol to glycerol 3-phosphate. Tissues that are low in glycerol kinase, like the muscle, or tissues that lack glycerol kinase entirely, like the adipose tissue, are not going to be able to use glycerol. At least not through the glycerol 3 kinase enzyme. Phosphoglycerol catabolism by phospholipases, which degrade and remodel the phosphoglycerol molecule. Each part of the phospholipid molecule is acted upon by a different enzyme, and it has a different or a specific or individual turnover rate. Due to presence of enzymes that allow partial degradation followed by resynthesis. This is unique about phosphoglycerols, that they are not necessarily broken down to the primary components or to the last to end up in an end product, for example, through a long pathway. Along the middle, the body may need the intermediate, so partial degradation will be followed by resynthesis. And of course, phospholipases hydrolyze phospholipids at many sites. For example, in this structure here, for a phospholipase, we have phospholipase A1 acts here. It releases a fatty acid from position 1. Phospholipase A2 acts here and releases this fatty acid from position 2. Phospholipase B can act at either side. Phospholipase C acts here, while phospholipase D acts here. Phospholipase A2 hydrolyzes the ester bond in position 2, as we said, of the glycophospholipid to yield a free fatty acid and a lysophospholipid. And then the lysophospholipid has two pathways. It is either reacetylated by an acyltransferase, and that is what we mean by degradation followed by resynthesis, or it can be further broken down by a lysophospholipase, which will remove the last remaining acyl residue, fatty acid, to form a glycophospholipase, which can be split into glycerol anabase. So this is our phosphatidylcholine. Phospholipase A2 acts here and removes this acyl residue. Now we have a lysophospholipid, phospholipid that lacks one acyl residue. This can be resynthesized. The whole phosphatidylcholine can be resynthesized again by an acyltransferase, which will replace the missed acyl-CoA to get a phosphatidylcholine choline again. However, this lysophosphatidylcholine has another fate. It can be attacked by another enzyme, which is a lysophospholipase, which will release this fatty acid acyl residue from this position to yield glyceryl phosphocholine, and this will be further hydrolyzed into glycerol 3-phosphate and a free choline base. This is your sphingolipids is from ceramide. So the parent molecule for sphingolipids is ceramide. This is the ceramide molecule. It consists of a sphingosine, which is attached linked through an amide link to a fatty acid, and in this position in the side chain R, it will be represented by hydrogen. When this hydrogen is replaced by phosphate, it will be ceramide 1-phosphate. When it is replaced by phosphocholine, it will be a sphingomyelin, and if this R is replaced by sugar, it will be a glycosphingolipid. And this is to show you central position of ceramide as a parent How is ceramide synthesized? Through four steps. First, serine combines with palmitoyl OA, catalyzed by the serine palmitoyl transferase. Carbon dioxide is released, CoA and phenol are released to form 3-ketosphingolene. 3-ketosphingolene is reduced to dihydrosphendosine, which is then acted upon by a dihydrosphendosine acyl transferase, so it will transfer and it will act on the acyl residue to the molecule to form dihydroceramide, which will be desaturated to ceramide. Sphingomyelin consists of a fatty acid plus sphingosine plus phosphoric acid plus choline. So to synthesize the sphingomyelin, we can use parent molecule ceramide. It will react with the phosphodiol choline, and the choline, of course, the phosphocholine will replace the hydrogen of the ceramide, and we will get sphingomyelin plus diacylglycerol. For glycosphingolipid synthesis, now we need sugars. Ceramide acts with UDP galactose to form galactoceramide, which is a serpocycle. And then epimerase will interconvert, of course, glucose, UDP glucose and UDP galactose. Sulfogalactosyl ceramide is formed by further reaction with a compound that is called BAPS. BAPS stands for 3-phosphoadenosine 5-phosphosulfate. It is a source for sulfate for the sulfogalactosyl ceramide. And then there is stepwise addition of activated compounds, UDP glucose and UDP galactose and cyanic acid to form gangliosides. So it starts by ceramide is a parent molecule. UDP and glucose and UDP galactose, as we said, are interconverted by an epimerase. UDP galactose will be reacting with ceramide with release of UDP to form a galactosyl ceramide. Galactosyl ceramide is a serpocycle. And then BAPS is added to form a sulfogalactosyl ceramide. And then as addition of neuroaminic acid of another molecule of galactosamine, addition of UDP galactose to form various forms of ganglioside GN2, GN1. The biomedical relevance of acylglycerols and sphingolipids. One important aspect is the lung surfactant. Lung surfactant as a compound is the protein mixture of mainly dipalmitoyl phosphatidyl choline with proteins, particularly surfactant proteins A, B, C, and D. Lung surfactant particularly plays a crucial role in reducing alveolar surface tension, preventing lung collapse. You need your alveoli to be like a balloon. When you inspire, when you take up your breath in, these alveoli are filled with air, and they are fully inflated. When you exhale, when you release oxygen or air from inside your lung to the outside, those alveoli will partially collapse, but they are not supposed to collapse completely. They must keep a certain degree of tension that prevents them from complete collapse, and then they will refill again by the second inspiratory cycle. For example, in neonates that are born prematurely, their body haven't had yet the chance to form adequate amounts of surfactant. They will have trouble with breathing, and they will experience lung alveoli and collapse of the lung alveoli because they are lacking the surfactant. They cannot keep their alveoli tense enough or inflate enough during the respiratory cycle. This is called neonatal respiratory distress syndrome, and it can be counteracted by infusing lung surfactant to prevent your infants to try to replace This is the lung surfactant to aid those neonates in breathing. A second condition that is relevant to our discussion today is multiple sclerosis, MS, which is a demyelinating disease that is characterized by loss of phospholipids and sphingolipids from the white matter, particularly the central nervous system. So this is a brain scan, an MRI. This is normal, and this is the abnormal part. You can see the whitish areas. The whitish areas represent plaques, multiple sclerosis plaques or areas in which phospholipids and sphingolipids are absent due to the inflammatory condition and demyelination or loss of lipids. The third and last condition that is related to our discussion is sphingolipidosis, which are historic diseases of sphingolipids. They are heterogeneous conditions. They are inherited conditions, so they are genetically determined. They are characterized by deficient lysosomal enzymes. So the enzymes that are needed for the breakdown or catabolism of those complex molecules are missing, and this will result in accumulation of sphingolipids. Gaucher disease and Fabry's disease are examples and are mentioned here because they are treatable conditions or enzyme replacement therapy. So the missing enzyme will be replaced, and this will affect the course of the disease immensely. Thank you very much, and this is the end of our discussion today.